A shocking explosion at Russia's secret missile testing facility has left the world questioning the reliability of its military technology. The catastrophic failure of the RS-28 Sarmat missile, ominously dubbed Satan II, has sparked intense debates over the effectiveness of Russia's hypersonic missile program and its broader military ambitions. Satellite images of the aftermath reveal severe destruction, suggesting a major setback for Moscow's nuclear modernization efforts. But is this just a technical mishap, or does it signal deeper cracks in Russia's defense capabilities? As tensions in the Russia-Ukraine conflict escalate, this incident raises a critical question: can Russia's military truly sustain its claim as a superpower, or are its weapons programs more smoke and mirrors than substance? Let's dive into the details and uncover the implications of this high-profile disaster. Initially, satellite imagery captured by Maxar Technologies revealed a massive explosion at Russia's Plesetsk Cosmodrome, located approximately 500 miles north of Moscow. The incident occurred at the Yubilynaya Silo launch site, which had been specifically modified for Sarmat missile launches. According to satellite data from September 21st, the explosion created a substantial crater measuring approximately 200 feet wide at the launch silo. Furthermore, the imagery showed extensive damage that was not visible in earlier September photographs. Multiple fire trucks were spotted near the destroyed silo. Moreover, small fires continued to burn in the adjacent forest area. The scale of destruction is stark. The explosion caused significant structural damage, with the crater situated directly over the underground silo, leaving the immediate launch pad area in ruins. Burning debris is strewn across the facility, and the surrounding forestland has suffered noticeable fire damage. Evidence points to the missile detonating within the silo itself, a catastrophic event that could have occurred either during ignition or immediately after an attempted launch. The damage pattern aligns with scenarios involving a major technical failure, casting doubt on the reliability of Russia's advanced missile systems and raising concerns about the safety of its testing protocols. The events leading up to and following the disastrous missile test paint a troubling picture of Russia's strategic weapons program. On September 19, 2024, the RS-28 Sarmat missile, also known as Satan II, was slated for a test launch from the Plesetsk facility. A notice to air missions was issued to secure the airspace around the test site, signaling preparations for the trial. However, the NOTAM was abruptly cancelled later that same day, indicating that the test had failed. By September 21st, satellite imagery confirmed the extent of the devastation. The photos revealed a massive crater at the launch silo, surrounded by widespread destruction. Analysts have since proposed several potential technical failures that could have caused the catastrophic event. Possibilities include errors during the fueling process, a first-stage engine malfunction, a command sequence failure, or fuel leakage during launch preparations. Each of these scenarios underscores serious vulnerabilities in Russia's missile development program. This incident marks the fourth consecutive failure in the Sarmat missile testing program, casting a shadow over Russia's ambitions to modernize its nuclear arsenal. The Plesetsk facility, a cornerstone of Russia's strategic missile forces, has been severely compromised, further delaying their plans. With each setback, questions grow louder about whether the Sarmat program can deliver the cutting-edge capabilities it has long promised, or if these repeated failures reflect deeper systemic issues within Russia's military-industrial complex. First of all, the RS-28 Sarmat represents Russia's most advanced intercontinental ballistic missile system, designed to replace the aging Soviet-era R-36 ICBMs. The missile's technical specifications reveal its formidable capabilities. The missile measures an imposing 35.3 meters in length. It has a diameter of 3 meters. Its launch weight is a staggering 208.1 tons, reflecting its capacity to deliver a payload of up to 10 tons. Designed for a maximum range of 18,000 kilometers. Despite its advanced design and formidable capabilities, the RS-28 Sarmat missile has encountered numerous technical hurdles, particularly with its propulsion system. At the heart of the missile is the Pu-99 rocket engine, an evolution of the Rod-274, which has been tasked with powering the next generation of Russia's intercontinental ballistic missiles. However, the complexity of this engine has introduced a series of challenges that have proven difficult to overcome. One significant issue lies in the shortened boost phase, a design intended to reduce the missile's exposure to early detection and interception. While this feature enhances its strategic stealth, it places immense strain on the engine, requiring an exceptionally high level of precision and performance in a very short time frame. Additionally, the engine has shown susceptibility to combustion instability. a condition that can lead to unpredictable and potentially catastrophic fluctuations in the combustion process. Structural stress concentrations within the engine components further complicate matters, as the intense forces during ignition and operation can lead to material fatigue or failure. Mechanical vibrations, a common challenge in high-performance rocket engines, present another critical concern. These vibrations can resonate through the missile structure, potentially interfering with guidance systems or causing damage to sensitive components. Compounding these issues is the challenge of maintaining fuel flow stability under the extreme conditions of launch, as any disruption could result in a loss of thrust or, in the worst-case scenario, an explosion. In contrast to traditional liquid-fueled missiles, the Sarmat employs a complex propulsion system that utilizes multiple combustion chambers with varying pressure levels. Therefore, this design choice creates potential risks of combustion instabilities and mechanical vibrations that can lead to structural damage. The Sarmat's development timeline has been marked by numerous setbacks. Similarly to other complex missile systems, the program has experienced significant delays and technical difficulties. The RS-28 Sarmat missile program, once hailed as a centerpiece of Russia's military modernization, initially showed promise with two successful tests. The first, conducted in December 2017 at the Plesetsk Cosmodrome, marked a significant milestone in demonstrating the missile's capabilities. This success was followed by another triumph on March 30, 2018, reinforcing optimism about the program's potential. However, progress soon gave way to a series of complications and setbacks that have cast doubt on the program's trajectory. Repeated delays in ejection tests, a critical phase to ensure the missile could properly exit its launch silo, slowed development considerably. These delays were compounded by a 2-year postponement of the initial flight testing phase, a timeline disruption that raised concerns about the feasibility of meeting deployment goals. Between 2020 and 2024, the program faced numerous test cancellations, suggesting persistent technical or logistical challenges. The situation reached a critical point with a string of 4 consecutive test failures, culminating in the catastrophic incident of September 2024. Each failure has eroded confidence in the system and underscored the formidable difficulties of achieving reliability in such a complex and advanced weapon. The missile's troubled development history stands in stark contrast to its predecessor, the Voyevoda R-36M2, which underwent 20 successful tests before deployment. The technical complexities, coupled with structural fragilities within Russia's missile design and manufacturing ecosystem, have significantly impacted the program's progress. The devastating explosion at Plesetsk Cosmodrome left an unprecedented impact on Russia's premier missile testing facility. A comprehensive analysis of the aftermath reveals both immediate structural damage and long-term environmental implications. The catastrophic failure of the RS-28 Sarmat missile test resulted in unparalleled destruction at the Plesetsk Cosmodrome, leaving a gaping crater 60 meters wide at the site of the launch silo. The scale of the devastation is stark, with the immediate launch area bearing the brunt of the explosion. The silo itself was obliterated, its structure reduced to rubble, and the surrounding area was littered with a sprawling field of debris. The impact extended beyond the launch pad, as satellite imagery revealed multiple fire zones in the nearby forest, highlighting the broader environmental consequences of the incident. Critical infrastructure within the facility suffered severe structural damage, with parts of the testing grounds rendered inoperable. Emergency response vehicles were observed at the site, including fire trucks and support teams, working to contain the aftermath of the explosion. The presence of ongoing fires in the surrounding forest further underscores the intensity of the blast and the challenges of managing the fallout. The pattern of destruction strongly suggests a catastrophic failure during the missile's initial launch phase. Whether due to a malfunction in the ignition process, a fuel system failure, or another technical issue, the explosion within the silo unleashed massive kinetic and thermal forces, decimating the area and disrupting testing operations. This incident not only represents a significant setback for the RS-28 Sarmat program, but also raises pressing questions about the safety protocols and reliability of Russia's advanced missile technology. The environmental repercussions of the RS-28 Sarmat missile explosion extend far beyond the immediate blast zone, raising alarm over the potential long-term effects on the surrounding area. The sheer magnitude of the blast, coupled with the missile's advanced nuclear capabilities, has created a multifaceted ecological crisis. One of the most pressing concerns is the potential contamination of groundwater with radioactive isotopes. If the explosion compromised the missile's nuclear components, radioactive materials could seep into the soil and leach into underground water supplies. This scenario would pose a grave threat to local water sources, potentially impacting both human populations and wildlife that depend on the area's natural resources. In addition to groundwater concerns, the risk of soil contamination looms large. The force of the blast and the subsequent debris field could scatter radioactive particles across a wide radius, rendering the land unfit for agricultural use and disrupting the delicate balance of the local ecosystem. These contaminated particles could also be carried by wind or surface runoff, spreading the environmental impact far beyond the site of the explosion. Atmospheric dispersion of fine particles from the blast adds another layer of environmental threat. If hazardous materials were released into the air, they could be transported over vast distances, endangering communities far removed from the test site. Airborne contaminants could settle in other regions, introducing new risks to human health and environmental stability. The explosion's impact on the local ecosystem and wildlife is equally troubling. Forest fires ignited by the blast have already disrupted habitats, and lingering contamination could lead to long-term declines in local biodiversity. Wildlife exposed to radioactive materials may experience genetic mutations, reproductive issues, or population collapse, further exacerbating the ecological damage. These environmental concerns are particularly alarming given the historical patterns observed at other nuclear testing sites worldwide. Such sites often exhibit long-term contamination, with ecosystems taking decades or even centuries to recover. The RS-28 Sarmat explosion has not only highlighted the immediate risks of advanced missile testing, but has also underscored the enduring environmental costs associated with such activities. The fallout from this incident serves as a sobering reminder of the far-reaching consequences of high-stakes military technology. The restoration of the Plesetsk facility faces substantial challenges. The immediate recovery efforts focus on containing any potential radioactive contamination and securing the damaged infrastructure. Based on previous incidents at similar facilities, the complete rehabilitation process could extend over several years. The damage at Plesetsk will undoubtedly affect Russia's hypersonic missile development program, as this facility serves as a crucial testing ground for their strategic weapons. Regardless of the immediate cleanup efforts, long-term environmental monitoring and remediation will require extensive resources and technological expertise. The incident's timing proves especially significant amid the ongoing Russia-Ukraine war update today, as it impacts Russia's ability to maintain its strategic missile testing schedule. Military analysts suggest that the facility's recovery could take substantially longer than initially estimated, given the complexity of the damage and the specialized nature of the infrastructure. The recent Sarmat missile failure marks a critical setback in Russia's nuclear modernization efforts. Indeed, the RS-28 program has experienced repeated delays since its inception, with the first test launch occurring 2 years behind schedule in 2022. The timeline for modernizing Russia's intercontinental ballistic missile arsenal, centered on the development and deployment of the RS-28 Sarmat, has been riddled with delays and setbacks. Initially slated for deployment in 2018, the program remains far from achieving its original goals. A closer look at the timeline reveals the extent of these delays. Initial testing, which was supposed to commence in 2020, did not occur until 2022. Combat readiness, originally targeted for 2021, remains incomplete, and the full deployment once expected by 2022 has been pushed to an indefinite future. Despite these substantial delays, Russian authorities have prematurely declared the missile operational, a decision that has raised eyebrows both domestically and internationally. This declaration came after only a single successful test, a stark departure from the rigorous testing standards historically applied to missile systems. For comparison, the RS-28 Sarmat's predecessor, the R-36M2, underwent 20 successful flight tests before being formally accepted into service. The ongoing delays and rushed operational status of the Sarmat carry significant strategic implications for Russia's nuclear deterrent. One of the most pressing concerns is the aging infrastructure of the country's existing missile systems. With the Sarmat's deployment lagging, Russia has been forced to extend its reliance on the Soviet-era R-36 missiles. These older systems require increasing levels of maintenance to remain functional, straining resources and diminishing the overall readiness of Russia's strategic forces. This reliance on aging technology undermines the operational efficiency and credibility of Russia's nuclear deterrence, especially in an era where modernization is critical to maintaining strategic parity with other nuclear powers. Additionally, Sarmat's problematic test record suggests that its premature acceptance into service could lead to operational risks, including potential reliability issues during a crisis. The decision to accept the RS-28 Sarmat, despite its testing shortcomings, marks a significant shift in Russian military policy, reflecting both the urgency of maintaining its strategic posture and the challenges of achieving technological breakthroughs. However, this shift also highlights the broader vulnerabilities within Russia's defense modernization efforts, as technical hurdles, delays, and resource constraints continue to hinder the development of next-generation systems. The implications of these challenges extend beyond the Sarmat program, raising questions about the sustainability and reliability of Russia's long-term military strategy. Meanwhile, Russia faces limited options for maintaining its strategic nuclear capabilities. The situation is complicated by structural fragilities within the missile design and manufacturing ecosystem, certainly exemplified by personnel shortages at Proton PMM, which manufactures the Sarmat's propulsion system. The delays impact Russia's ability to maintain warhead parity with the United States, a crucial strategic objective. Although producing additional land-based ICBMs remains an option, Russia might need to consider uploading warheads from storage across existing delivery systems. The setbacks have prompted consideration of alternative approaches, including extended service life for existing systems, increased investment in submarine-based deterrence, development of new delivery platforms, and modification of current missile designs. The technical viability of these alternatives remains debatable, yet Russian leaders continue substantial investments in novel delivery systems meant to evade missile defenses. The situation is further complicated by the destruction of the specially adapted Yubilynaya test silo, which may cause additional delays in Sarmat's testing and eventual introduction into service. Military experts have conducted extensive analysis of the recent Sarmat missile failure, revealing fundamental flaws in Russia's hypersonic missile development program. Their findings point to multiple technical issues that extend beyond a single failed test. The root cause of the RS-28 Sarmat missile's catastrophic failure appears to lie within its first-stage booster system, a critical component of the missile's propulsion architecture. Preliminary technical analysis suggests the failure resulted from one or more of several interconnected issues. One possibility involves a malfunction in the step liquid engine, a design intended to optimize thrust by varying pressure levels and fuel mixtures. While innovative, this design introduces a high risk of combustion instability, where uneven combustion patterns can create dangerous oscillations and unpredictable performance. Another likely contributing factor is the occurrence of mechanical vibrations, exacerbated by the intense stresses experienced during the missile's ignition and initial ascent. These vibrations, if resonant with the missile's structural frequency, can lead to material fatigue or outright structural damage. Compounding these issues are potential irregularities in fuel flow, a critical parameter for maintaining engine stability and thrust. Disruptions in this flow can lead to uneven performance or even catastrophic failure. The missile's structural design also presents vulnerabilities. The Sarmat employs a lightweight orthogrid structure to reduce overall weight and improve efficiency. However, this design may render the missile particularly sensitive to asymmetric loads, such as those caused by uneven thrust or external forces during launch. Such sensitivity could result in structural deformation or failure under extreme conditions. A broader technical analysis has highlighted systemic vulnerabilities across the missile's design architecture, revealing critical challenges in several areas. The propulsion system itself faces significant hurdles, including complications associated with its multiple combustion chambers and the precise balancing required to prevent instability. The orthogrid structural framework, though innovative, appears to trade robustness for weight reduction, leaving it more susceptible to mechanical stress. Liquid fuel management also remains a pressing concern, with stability issues posing risks during both storage and use. Finally, the missile's cold launch system, a mechanism designed to eject the missile from its silo before the main engine ignites, has shown reliability concerns, further complicating the Sarmat's operational profile. The propulsion system stands out as particularly problematic. Its reliance on varying pressure levels and fuel mixtures to maximize efficiency makes it inherently susceptible to combustion instabilities. These instabilities not only compromise engine performance, but also generate dangerous vibrational loads, which can cascade into broader mechanical failures. Together, these technical shortcomings paint a picture of a highly advanced but deeply flawed system where ambitious innovation has outpaced practical reliability. The Sarmat's ongoing difficulties underscore the challenges of achieving a balance between cutting-edge technology and operational dependability, a challenge that Russia's missile development programs continue to grapple with. Looking ahead, Russia's hypersonic missile program faces substantial obstacles. The development team must address several critical challenges. First, The manufacturing ecosystem shows significant strain, markedly evident in the personnel shortages at Putin PM, the facility responsible for producing the Sarmat's propulsion system. This workforce limitation fundamentally impacts production capability and quality control. Second, the missile's testing protocol deviates from established standards. Whereas the previous Voyevoda R-36M2 underwent 20 successful tests before deployment, the Sarmat has been fast-tracked into service with only one successful test. The technical assessment indicates that Russia's attempts to optimize the missile's boost phase may have created unnecessary complications. Essentially, these modifications have resulted in increased system complexity, higher structural stress levels, greater risk of mechanical failure, and reduced overall reliability. Military analysts suggest that Russia's strategic forces face a complex dilemma. The current situation might compel Russian leaders to take earlier crisis response measures than typically warranted. This consideration becomes particularly relevant in light of the ongoing Russia-Ukraine war update today. The technical vulnerabilities identified in the Sarmat program occasionally manifest in other aspects of Russia's missile development efforts. For instance, similar issues have been observed in the testing of other strategic weapons systems. These recurring problems raise questions about the overall health of Russia's military-industrial complex and its capacity to maintain advanced weapons programs. A comprehensive analysis of intercontinental ballistic missiles reveals striking differences between Russia's RS-28 Sarmat and other global strategic weapons. The first thing to remember, the Sarmat's physical specifications set it apart from its contemporaries. The RS-28 Sarmat missile, one of Russia's most ambitious military projects, boasts specifications that position it as a formidable threat on the global stage. With a length of 35.3 meters and a weight of 208.1 tons, the Sarmat far surpasses many of its counterparts in terms of scale and destructive potential. For comparison, the U.S. Minuteman II, one of the United States' most well-known intercontinental ballistic missiles, measures only 18.2 meters in length and weighs 36 tons. Additionally, the Sarmat's impressive range of 18,000 kilometers outstrips the Minuteman II's reach of 13,000 kilometers, providing Russia with the ability to strike virtually any location on Earth. Moreover, the Sarmat is capable of carrying up to 15 warheads. Thanks to its integration of multiple independently targetable re-entry vehicles, a key feature of modern ICBMs that allows the missile to engage multiple targets simultaneously. In contrast, the U.S. Minuteman II carries a single warhead. This advanced capability enables the Sarmat to significantly enhance Russia's strategic nuclear deterrence. However, despite these formidable specifications, the RS-28 Sarmat program has faced significant reliability challenges. A stark contrast emerges when comparing the testing history of the Sarmat with that of its U.S. counterpart, the Minuteman II. The Minuteman II system has enjoyed decades of reliable service, with approximately 400 active missiles in operation and regular successful test launches conducted multiple times each year. The missile's proven track record is a testament to its dependability, having undergone rigorous testing protocols that have consistently confirmed its operational readiness. In stark contrast, the Sarmat program has had only one successful test since its inception and has been marred by 4 consecutive test failures. This troubled testing history has raised serious concerns about the missile's overall reliability, especially given the rushed deployment despite its limited testing record. For context, its predecessor, the R-36M2, underwent 36 successful tests before being formally deployed, setting a high standard that the Sarmat has yet to meet. From a financial perspective, the cost of developing and deploying such advanced missile systems is substantial. For example, the United States' next-generation interceptor missiles, integral to their defense strategy, cost an average of $498 million per interceptor, with a total program cost of $18 billion for 31 new interceptors. These missiles represent a significant investment, reflecting the high financial stakes involved in maintaining a cutting-edge defense capability. Furthermore, the potential costs of deploying a single ICBM with a conventional payload in an urban center could amount to $18.8 billion, a figure that rises dramatically to $837 billion if a nuclear payload is used. These astronomical numbers underscore the enormous financial burden associated with both the development and potential deployment of such powerful weapons. In terms of strategic approaches, the United States and Russia have adopted differing methodologies to maintain their deterrent capabilities. The United States has focused on deploying fewer warheads per missile but compensates by maintaining a larger number of delivery vehicles and regularly modernizing its missile systems. This strategy is complemented by the ground-based Midcourse defense system, which boasts 44 interceptors stationed in Alaska and California. Despite its mixed testing record, with a 50% success rate in scripted tests, the GMD system reflects the United States' broader focus on defensive capabilities to safeguard its interests. In contrast, Russia's approach centers on the use of heavy ICBMs, such as the Sarmat, equipped with multiple warheads per missile. This strategy results in a reduced number of delivery platforms, reflecting Russia's budget-conscious approach to missile development. While this method provides Russia with significant offensive power, it also carries the risk of over-reliance on a small number of large, complex weapons systems, whose reliability remains unproven. The differing strategies of the two nations illustrate the complex landscape of global nuclear deterrence. While both countries face immense technical and financial challenges, the continued development of these missile systems highlights the growing stakes in the global arms race. As the reliability of advanced missile systems such as the Sarmat remains uncertain, questions surrounding the sustainability and effectiveness of such high-stakes programs will continue to shape military strategies worldwide. The catastrophic failure of Russia's hypersonic missile test has fundamentally altered the landscape of nuclear deterrence. At present, this setback raises profound questions about Moscow's ability to maintain its strategic nuclear capabilities. The catastrophic failure of the RS-28 Sarmat missile test has reverberated throughout the global nuclear deterrent framework, creating significant challenges for Russia's ability to maintain strategic parity with the United States. This failure highlights the fragility of Russia's nuclear modernization program, which, despite its ambitious goals, has struggled to meet critical milestones. The current situation presents a complex matrix of strategic implications, each carrying profound consequences for Russia's military capabilities and its position on the world stage. One of the immediate impacts of the failed test is the compromised deterrence capability of Russia's nuclear arsenal. The Sarmat, intended to be a cornerstone of Russia's nuclear force, has proven unreliable, which directly undermines its ability to project credible deterrence against potential adversaries. This failure necessitates a reassessment of Russia's nuclear posture, as it must now grapple with the uncertainty surrounding its newest and most powerful missile system. Equally concerning is the diminished second strike readiness that this failure indicates. Russia's nuclear doctrine heavily relies on the principle of assured retaliation, whereby the country maintains the ability to launch a devastating second strike in response to a first nuclear attack. The Sarmat, with its multiple warhead capacity and long range, was seen as key to ensuring that readiness. However, the recent failure raises questions about the missile's reliability and the readiness of Russia's broader nuclear deterrent forces. As a result, Russia's second strike capabilities may be extended in vulnerability, leaving the country with fewer options in the event of a nuclear crisis. Strategic parity between Russia and the United States is also under increasing pressure. The Sarmat was expected to provide Russia with a significant advantage over the US in terms of missile range, payload capacity, and warhead capabilities, thereby maintaining a semblance of balance in nuclear deterrence. However, the ongoing setbacks with the missile program, combined with the superior testing and operational reliability of US systems, could lead to a potential imbalance in strategic capabilities. This imbalance, should it persist, would erode Russia's position in arms control negotiations and undermine its ability to assert itself as a leading nuclear power. This failure is all the more significant given the current geopolitical climate. It comes at a time of heightened global tensions, particularly due to the ongoing war in Ukraine, which has escalated East-West relations to their most dangerous point in over 60 years. The international community is closely watching how Russia responds to these setbacks, with implications for both regional security and global stability. In an era of rising military competition and nuclear uncertainty, Russia's difficulties with the Sarmat program are likely to have far-reaching consequences, both for its strategic posture and for the global security landscape as a whole. The ongoing failures of the RS-28 Sarmat missile program have significantly damaged Russia's nuclear credibility, which is crucial for maintaining its position as a global power. In the long term, these repeated technical setbacks are likely to erode Moscow's ability to project a credible nuclear deterrence. One of the most concerning aspects is the continued failure to achieve reliable test results, with 4 consecutive failures casting doubt on the missile's effectiveness. Additionally, the delayed deployment of the Sarmat, which was initially scheduled to be operational years ago, raises further questions about the program's viability. These unresolved issues not only complicate Russia's military strategy, but also undermine the messaging surrounding its nuclear deterrence. The International Institute for Strategic Studies has warned that Russia's continued reliance on its aging S-18 missiles could exacerbate readiness concerns. The S-18, which is approaching the end of its operational lifespan, has already been in service for decades, and maintaining these outdated systems is becoming increasingly difficult. This situation is especially critical as Russia continues to emphasize the importance of its nuclear capabilities in diplomatic dialogues, making any sign of weakness or unreliability in its missile programs a potentially costly blow to its standing on the global stage. These technical and strategic challenges could ultimately undermine Russia's ability to credibly deter potential adversaries and project power in the nuclear domain. The consequences of the failed Sarmat test go far beyond the immediate technical shortcomings, with broader implications for Russia's military readiness. The devastation at the Plizhitsk Cosmodrome, located in the Arkhangelsk region approximately 800 kilometers north of Moscow and surrounded by dense forest, represents a significant blow to the Sarmat program. The destruction at this key testing facility will undoubtedly have far-reaching effects on the development and deployment of Russia's advanced missile systems, triggering a cascade of challenges for the nation's nuclear forces. One of the most immediate operational impacts is the delayed introduction of new missile systems. With critical infrastructure compromised, the timeline for the Sarmat's deployment will be pushed even further into the future, slowing down Russia's efforts to modernize its nuclear forces. This delay forces Russia to extend its reliance on older, less advanced missile systems, which not only raises maintenance and operational concerns but also limits the country's overall flexibility in responding to emerging threats. The continued dependence on aging platforms, particularly the S-18, compounds the risks, as these systems are increasingly prone to wear and technical difficulties, reducing their effectiveness. As a result, Russia's overall operational flexibility is diminished. The delay in rolling out advanced systems like the Sarmat leaves fewer options available for strategic deployment, limiting Russia's ability to adjust quickly to new challenges or changes in the global security environment. The situation becomes more complex as Russia must balance these challenges while maintaining its nuclear deterrent posture. The International Institute for Strategic Studies analysis indicates that scrapping the Sarmat would make it difficult for Russia to maintain warhead parity with the United States, a crucial strategic objective. At this instant, the failed test has broader implications for NATO's strategic planning. The alliance must now reassess its deterrence framework, considering both Russia's technical difficulties and its continued nuclear messaging. This reassessment becomes particularly significant as NATO works to maintain a robust strategic deterrent, including the modernization of its nuclear triad and missile defense systems. The situation presents a paradox for global security. On one hand, it indicates that Russia's most advanced nuclear missile may not be as operationally reliable as Moscow has portrayed. Conversely, a failing Russian nuclear infrastructure could increase the likelihood of miscalculation or accident. This dynamic creates new challenges for strategic stability, as a Russia that feels cornered might be more prone to considering nuclear options out of desperation. Because of these developments, Western military analysts suggest that while the failure of the Sarmat test reveals weaknesses in Russia's strategic nuclear capabilities, NATO cannot assume that Russia's overall deterrence has been significantly diminished. The alliance must continue maintaining a robust strategic deterrent, while ensuring its response mechanisms can address potential tactical nuclear threats. Facing mounting technical challenges and repeated setbacks, Russia's hypersonic missile program stands at a critical crossroads. The latest test failure of the RS-28 Sarmat has prompted a comprehensive reassessment of the nation's strategic weapons development strategy. The Russian military-industrial complex must now navigate several potential paths forward. After all, the Sarmat program's viability remains crucial for maintaining strategic deterrence capabilities. The Kremlin's options include continuing the current Sarmat development with enhanced testing protocols, reverting to modified versions of existing missile systems, exploring alternative delivery platforms, and developing new propulsion technologies. By comparison, the Makeyev Rocket Design Bureau, responsible for the Sarmat's development, faces significant technical hurdles in addressing the missile's propulsion system issues. Rather than abandoning the program entirely, Russian authorities have indicated their commitment to persisting with the Sarmat development. The Russian military-industrial complex is currently grappling with significant challenges in efficiently distributing its resources, particularly within the missile design and manufacturing sectors. Over time, these difficulties have revealed structural weaknesses within the missile production ecosystem, which have emerged as key bottlenecks in the overall development process. One of the most pressing issues lies in the manufacturing capacity, with critical shortages in skilled personnel at the Proton PM facility, which plays a pivotal role in producing key components for the missile program. The facility also faces limited access to specialized materials and components, which further hampers production. Additionally, production lines are strained, making it increasingly difficult to meet the ambitious targets set for missile output. Compounding these issues are ongoing quality control challenges, which risk compromising the overall reliability of the systems being developed. In parallel, the technical expertise necessary to overcome these hurdles is in short supply. The workforce requires extensive training to address the evolving technological demands of missile development, and there are considerable challenges in transferring specialized knowledge across generations of engineers and technicians. The Sarmat program's resource requirements must now compete with other strategic priorities. Whether Russia can maintain its ambitious modernization goals remains uncertain, as the program has experienced 4 successive test failures. Nevertheless, Russian authorities maintain their commitment to the program, as evidenced by the state contracts signed for the manufacture and supply of the Sarmat strategic missile system. The technical viability of the current development path faces increasing scrutiny. In addition, the program's challenges extend beyond mere technical issues to encompass broader strategic considerations. The missile officially entered operational service in September 2023 as the world's longest-range and most powerful extant ICBM system. Otherwise, the repeated test failures have raised questions about the system's reliability and operational readiness. Lastly, the program's trajectory will significantly influence Russia's strategic deterrent capabilities. Unless substantial progress is achieved in addressing these fundamental challenges, the Sarmat program may face additional delays or require major redesign efforts. The situation becomes particularly significant as Russia continues its military operations, with the Russia-Ukraine war update today highlighting the importance of maintaining strategic capabilities. Russia's latest Sarmat missile test failure marks a major setback in its nuclear modernization efforts. Technical flaws, particularly in the propulsion system and structural integrity, along with the destruction of crucial testing infrastructure, raise doubts about Russia's ability to maintain its nuclear capabilities. The repeated failures erode the credibility of Russia's nuclear deterrence and delay its missile development, impacting its strategic position against other nuclear powers. This failure exposes deeper problems within Russia's strategic weapons development, suggesting a long recovery period ahead. With these setbacks, how will Russia's nuclear deterrence evolve, and can it recover its credibility on the global stage? Let us know your thoughts in the comments below. Thanks for watching.